Okay, G students, Assalamu alaikum. After completing the quantum physics, we're going to start the nuclear physics. Here are the course outlines for that, right? You can read them. I'll be sharing this file with you. Okay. So, yes, let's start with the very basic concepts to start this chapter, right? Okay, atom is this is the smallest particle of an element. You know that, right? Atom consists of two parts: the nucleus and the shell. Right? Nucleus is many times smaller than its own atom. It is actually like 10 to the power 4 times smaller than the atom. And these are the very basic informations that you have been already studying since long, right? They are written there. The atomic number, you already know about it. The mass number, you already know about it. The formula of the mass number and how do we calculate the number of neutrons. You have studied it in your O levels and in AS, right? Okay. So what is an isotope? You also already know about it, right? But I have given you some examples of like hydrogen, whose number of first isotope is protium and then deuterium and then tritium. And their electron number, proton number, atomic number, neutron number, and mass number is given, right? So what is radioactivity? You also already know about it, right? You have done it in detail in your AS. So and that's yeah, then you also know about it, like what is an electron, what is a positron, a proton, a neutron, and what is a helium nucleus, and what is transmutation. It is a conversion of one element into other type of the element, right? Parent nucleus is which breaks down, and the daughter nucleus which is newly formed nucleus, right? And this breakdown of nucleus called nuclear decay. You have done it. These, and you have also done alpha, beta, and gamma decays in your AS. But let me just remind you, let's say we have an element X whose atomic number is Z and mass number is A, and alpha decay is if a helium nucleus is emitted from it. So 2, 4. So what's going to happen? The new element Y is going to be formed as, so like Z minus, sorry, there is a mistake, and that is, so here is mass number and here is atomic number. So it will be like A minus 4 in the mass number and Z minus 2 in the atomic number. Right, students? So this is called the alpha decay. The beta minus and beta plus decay you are aware of. And that is like this. The elements are like same, A and Z, A, Z. And if beta minus is emitted, then it's going to be beta minus 1, 0. And if it beta plus, sorry, if beta plus is emitted, we are first talking about beta plus, then it's going to be 1, 0. And for beta minus, it's going to be beta minus 1, 0. Then the element which is going to be newly formed is going to be this thing, that here it's going to be A, but Z minus 1, but here it's going to be A, Z plus 1, right? Okay, and what about in gamma decay? You know, okay, the element just remains same. Like if this is plutonium, then plutonium is also converted into same plutonium, but it emits a high energy electromagnetic wave, which we call as gamma ray, right? Its frequency is typically 10 to the power 20 hertz. Okay, friends. So this was just a quick revision of the O levels and AS thing. Now let's get to some A2 stuff after this thing. Okay, students. SI unit of energy is joule. The smaller unit is electron volt, right? Okay. So let me take a minute to come back to you. I have to just send a video lecture to you. So yes. Okay. So I'm back. Electron volts. We know that electron volt is a kinetic energy. This is the definition of electron volt. Electron volt is the kinetic energy obtained by the electron due to a potential difference of 1 volt. The conversion factor is this, you know, and you also know that if we have to convert these joules into electron volts, then we're going to do what? We're going to divide this thing this number by this conversion factor. So we are going to get the answer into electron volts. And if we want to convert, this 3 electron volt joules into 3 electron volts into joules, so we are going to multiply the same um, conversion factor, and we are going to get the answer in joules, right? And for million electron volts, the exponent of 10 changes to this, right? So if you want to convert this 1.6 million electron volts into joules, then we are going to definitely multiply this by this number, right? Okay, now some very important informations are going to be there, which are actually given in exam. Actually, they are given in exam like, let me show you how. Like these are the questions where these things are given. Let me show you. Yes. So these information, mass of the beta particle, mass of neutron, and mass of proton in terms of U. Now, what is U? Let me tell you. U is basically the atomic mass unit, right? So atomic mass unit is basically 1.66 times 10 to the power negative 27 kgs, right? Charge on an electron, it is, this of negative sign, and the charge on a neutron is 0. Charge on proton is this, and the mass of electron is, students, this. This will be given in data booklet. And the mass of neutron is this, here is 7 kgs. This will also be given. Charge on the charge on proton, sorry, mass on the proton, mass of proton in terms of U is 1.007 U, and the mass of electron in terms of U, it is 5.5 into 10 to the power negative 4 U, right? And the mass of neutron in terms of U, it is like 1.009 U, right? So these are the very important informations for the upcoming chapter. Okay, now, if we talk about the quantities conserved in the nuclear reaction, they are momentum, proton number, nucleon number. And this important thing is neutron number is not conserved. It is never conserved, right? And one more thing is mass energy is conserved. Neither the mass nor the energy can be alone conserved, because during the reaction, some of the mass during the nuclear reaction is converted into energy. So we rather call it mass energy is conserved, right? Okay. So now, what are the properties of radioactive decay? Radioactive decay is turns a spontaneous phenomena. First of all, what does it mean? What does it mean by spontaneous phenomena? Because spontaneous means natural, so it does not depend on the environmental conditions like temperature or pressure. And it also is independent of the number of the nuclei available, right? And the second property of the radioactive decay is randomness, right? Each nucleus in the sample has the same probability of decaying. We cannot say that the nuclei in the outer layer are more probable to go into decay phenomena and the lower one are less probable. They are equally probable to decay, right? And it is also unknown that when a specific nucleus is gonna decay, right? So here are the examples of this thing, like radiation in the GM tube has the same average value at different temperatures. If the temperatures are different, again the value is same. Radiation will also read the same average value for the same element with different concentrations. So number of nuclei, they don't affect it. If one nucleus decays on 3 nanoseconds, then it may be possible that the 3 nuclei decay in 6 nanoseconds, right? Okay, so any nucleus can decay at any time, right? Okay. So now let's talk about Einstein's mass energy equation. You already know about it. It is like delta equals to mc square, where m is the rest mass right? C is speed of light, which you already know the value of, right? And delta is the energy, right? So what is rest mass? Rest mass is the mass of an object when there is neither any absorption of energy or energy emission, right? Energy absorption or energy emission, right? Okay. So what is mass defect? The difference in the mass of the independent isolated number of the nucleons and the mass of the nucleus formed by the same number of nucleons. Now, how can you understand it? Mass effect is a new concept for you. Let me start. Okay, let's talk about carbon nucleus, right? Okay. Einstein told us about this concept. He said, let me tell you that thing before starting this concept. Einstein said that if there is a mass and it absorbs energy, then mass is going to increase m plus something. So this is going to be the newer mass after absorbing energy, right? And Einstein also said that if there is a mass and it, instead of absorbing energy, it releases energy or emits energy, then what's going to happen? This mass is going to not going to remain that, it's going to actually reduce. So it's going to be m minus something, the newer mass. So this was Einstein's concept on absorption and emission of energy, right? So using that concept, he told us about this thing, mass effect. Okay, so let me tell you how. Let's take the example of carbon. You know, since carbon nucleus contains 12 nucleons, out of which 6 are protons and 6 are neutrons, right? So, the mass of the neutron I just told you is 1.009 U. You don't have to remember this mass, it will be given. So mass of 6 neutrons is going to be 6 times 1.009 U. So it's going to be what? 1.054 U, right? Okay. So the mass of one proton is 1.007 U. So the mass of 6 protons is going to be 6 times 1.007. So it's going to be what? 1.042 U. So the total mass of 12 independent isolated nucleons, it's going to be this thing, at 1.054 plus 1.042 U, and it's going to be 1.096 U, right? So that is the mass of the 12 independent protons and neutrons, which are not like I was talking about this thing, like there are 12 independent things. They are not inside the nucleus, right? Like they are proton, one proton is here, one is here, three, and then four, and then five, and then let's say six. And then let's say the neutrons are like, again, six in number, like one, two, three, four, five, and six. So their mass is this 1.06, 1.096 U. Okay. But when these nucleons are combined together to form this nucleus, this is what? Nucleons. And this is what? The nucleus formed by the 12 nucleons, right? Then this mass was done, right, students? Okay, 1 minute. I think I've done some calculation mistake, and that is this. This is going to be 6.054, and this is going to be 6.042. So this is some calculation mistake, that this number and this number, they are going to be 6.0, and when we are going to add them in the next step, it's going to be 6.054, 6.042, so it's going to be 12.0964, right? So I'm going to write here as well. It's going to be 12.0964 U, the mass of the 12 nucleons. And when we take the carbon atom, when we weigh it, its mass is 12 U exactly. So that's the difference. So actually, it means that when these nucleons, they're going to combine together to form this nucleus. Why is the mass decreasing from 12 point, from this 12.0964 U to 12 U? Why is this mass decreasing? Einstein told us the reason about this thing. Einstein said that energy is released here when the nucleus is formed. So he said that when the nucleus is broken, the energy is absorbed, right? So he told us that the same energy is absorbed. Okay. Okay, students. So sorry for the delay. That you know, energy is gonna be absorbed when the nucleus is broken, and the energy is released when the nucleus is formed. So that's why there is a change in mass. So this change in mass, that was like 12.0964, sorry, 0.096 U minus 12, that is like 0.096 U. This is the mass effect of the carbon atom, right? So you can see the mass of the isolated independent nucleons is more, it is more than the mass of the carbon atom, right? So the difference in mass is going to be this 12.096 U minus 12 U. So it's going to be 0.096 U. That is the mass effect of carbon atom, right? Other examples are like uranium 235. We can see that the mass of the nucleus is this thing, 235.123 U. It's a reality. And if we calculate the total mass of the nucleons from which this nucleus is made of, it's going to be like mass of one proton is 1.007 U. So if we talk about like uranium 235, 92, it means there are 92 protons. So the mass of the 92 protons is 92 times 1.007. So if we like calculate it, it's going to be this. So 92.644, 92.644 U, right? And if we talk about the number of neutrons, and they're going to be like 235 minus 92. So 235 minus 92 is just 143 neutrons. So if you like talk about the mass of 143 neutrons, then it's going to be mass of one neutron is 1.009 U. So one mass of 143 neutrons is going to be 143 times 1.009. Then it's going to be, students, 144.287 U, right? And the total mass of the 235 nucleons is going to be this, like 92.644 U plus 144.287 U. So it's going to be what? 92.644. So it says 236.931 U. So this is the mass of the independent nucleon. So if we calculate the mass difference, like mass of the independent nucleons, which is like 236.931 U, and then the mass of the nucleus, which is 235.123 U, then students, it is just 1.808 U. So that is the mass effect of uranium nucleus, right? So now let me like come back to the definition of the mass effect, which was this thing. Okay, let capital M is the mass of the n number of neutrons, and small m is the mass of the nucleus, where n is the number of nucleons. Then okay, what mass is more? Capital M is always more than small m, and this capital M minus small m, which is delta m, is called what? Mass defect, right, students? So let's go further. Okay, binding energy. Binding energy is basically the energy related to the mass effect. Like it is the energy absorbed or to the nucleus to separate the nucleons from the effect of nucleus to infinity, right? And how do we calculate it? We calculate it using the Einstein's mass energy relationship, where delta M is what? Delta M is mass effect, and delta E is what? It is the total binding energy, right, students? And what is binding energy per nucleon? This is another definition. It is asked in exam as well. Binding energy per nucleon is basically the binding energy of a nucleus when we divide it. Total binding energy when we divide it by the number of nucleons. We get what? We get this thing. Binding energy per nucleon, right? Now, binding energy per nucleon is not defined for a single nucleon, like a protium nucleus of hydrogen has only one nucleon or one proton. So binding energy is not defined because the binding energy can only be defined if there is something to bind with a nucleon, right? So if there is a single nucleon and there is nothing to bind with, then binding energy is not defined. Binding energy per nucleon is not defined, right? Okay. So examples: carbon. So students, we saw that the mass effect for carbon was like 12.096 minus 12 U. So it was like 0.096 U. So if you want to like calculate the binding energy of carbon, it is going to be delta E is equal to delta M times C square. So what is delta M? 0.096, and U is 1.66 times 10 to the power negative 27, and we have to convert this u into like kgs, and then we're going to put the value of the speed of light and take the square of this thing. So it's going to be, yes, so let me do it for you. 3 times 10 to the power 8 square times 1.66 times 10 to the power negative 27 times 0.096. So students, it is like these many joules, 1.43 times 10 to the power 11, negative 11 joules, right? And if we want to convert it into million electron volts, then, we can do the conversion factor. We can put the conversion factor here. So we're gonna like divide this thing by this number, and we are gonna get what? Yes. So students, 89.64 million electron volts energy is absorbed to break down the carbon nucleus, right? Okay. Now, what about uranium? Since we got it that the mass effect calculated for uranium was like this, 1.808 U previously. And if we want to calculate the binding energy, then it's going to be this thing, delta M times C squared. So it's 1.808 U is conversion factor is this. And then this is speed of light. Right, so if we do it, then we're going to get 2.7 times 10 to the power negative 10 joules. So if we like divide it, by that number, the conversion factor, to convert it into million electron volts, then we can see what's going to happen. Since it is 1688, 1688, 1688 million electron volts, right? The same way you can do it with lanthanum nucleus, like what is the mass of the lanthanum nucleus? Since it is this, so since you can do it with this, like mass is of the nucleus is 138.955 U, and then you can calculate the mass of the protons is like 57 number of protons, and we multiply it by 1.007, plus whatever are the neutrons are like 139 minus 57, and the mass of one neutron is like 1.009. So if you do it, we're gonna have what? Let me calculate it for you. So since it's gonna be 140.137 U. So since you can then calculate the mass effect, it is like 140.137 minus the mass of the nucleus, which is 138.955 U. So since it is 1.182 U, so now we can calculate the binding energy as well, students. It is like delta M times C square. So delta M is 1.182, and the conversion factor to convert this U into kgs is this, and then C square is 3 into 10 to the power 8 whole square, right? So it's gonna be what? Let me see. So students, it's gonna be this 1.76 times 10 to the power negative 10 joules, and the conversion factor to convert this energy into million electron volts, right? So students, you can do it with molybdenum, you can do it with nitrogen yourself, you can do it with oxygen yourself. All right, and then we are going to start from here next time, right? So I stop here for the next lecture coming soon. Okay, students, then Allah Hafiz.